Alright, question number 9 on the final review is another rotational problem. So what we have for this one, we have a solid disk with a radius, and it should say the disk is rolling, but it says the hoop is rolling, so ignore that. So we want to find translational kinetic, rotational kinetic, and the height. So again, another conservation of energy problem. So to start off, the formula for inertia of a disk is 1/2 mr squared. So we end up again with radius 20 centimeters, which has to get changed to 0.2, and it has a translational speed of 2 meters per second. So step 1, what's the translational kinetic energy? That formula is always 1/2 mv squared, no matter what. So the problem tells us that the mass is 1, and then we know the velocity from the problem is 2, so that ends up being 1/2 times 1 times 2 squared, which ends up being just 2 joules of energy. So translationally, as it's rolling, it has 2 joules of energy. And that is the formula for all shapes. So again, translational kinetic energy, always 1/2 mv squared no matter what. Rotational is the one that's a little different because that is based on the inertia and the angular speed. Now what you end up with, the rotational kinetic energy has the form of 1/2 I omega squared. Just like the previous problem, what you can do is end up lopping off some of the variables because you can plug in for I, which becomes 1/2 mr squared, and then you plug in for omega of v squared divided by r, and that's also squared, so you end up canceling out the r squareds. You end up with mv squared and then with a certain value for coefficient in front of it. So that's 1/4 mv squared. So that is also always true for a disk. You always have 1/4 mv squared, so we plug in 1/4 times 1 times 4, ends up being 1 joule. So at this instant, at the very beginning, with the two types of energy that we have a total energy of 3 joules initially. Now the part C is asking how high it's going to roll. And we're talking about how high it's going to roll, so we need to use different energy values. So energy total is going to be the sum of translational plus rotational kinetic energy. So that is going to end up being R2 plus R1 that we already had. And that's going to tell us the amount of energy that we have present in the system at all times. Now, when the question's asking how high is it going to roll, that means it is not moving anymore after that part. So the height it's going to roll means that at that instant, it's only going to have gravitational potential energy and nothing else. So we know the total energy at that point is 3 joules. So we can set that equal to the gravitational potential energy of mgh. We can use that information then to solve for the actual value for height. So 3 is equal to 1 times 10 times the height, which is going to be 3/10, or 0.3 meters. Now there's an important distinction that we have to make between height and far. So if a question says, to what height does it roll? The height that it rolls is the vertical distance. How far it rolls would end up being how far up the slope it actually goes. So height is from ground vertically upward when we draw a line. Delta x is going to be the distance that's going to go up the ramp on the plane of it. So again, height is h. How far is delta x? So if you get a problem and they ask you how far does it roll, you are trying to find delta x using trig. If they ask you how high it goes, you are finding h using potential energy.